Thanks, Fabrizio, for being with us virtually. Now we go to the practical part. So this morning you have seen all the theory and the algorithms with the combination of Sentinel-2, Sentinel-1, so optical and radar for agricultural applications. Now we go to the practical part. First, Fabrizio Ramoino, a colleague of ours in ESRIN, who's working since many years on land applications and agricultural applications, will show you how to use SNAP, so this ESA software, ESA toolbox for Sentinel data, and you will see the estimation of leaf area index using I think Sentinel-2 data. Is it correct, Amalia? Yeah, and you will have first a demo by Fabrizio, then you will be asked to repeat the exercise by yourselves. We have seen that these computers with 16 GB RAM are still slow if you have too many data to process, so you shouldn't do the processing for all the 16 datasets. Is it 16 datasets that you will get? So don't do it, for otherwise it will take forever. So just limit to a few data, and Amalia will guide you through the exercise in order to repeat what Fabrizio did. So Fabrizio will show probably the result for 16 datasets. You should do it just for a few datasets in order not to get too slow. Thanks, Fabrizio. The floor is yours.
Thank you, Francesco. Welcome to everybody. So as said Francesco in the first part, there will be a short refresher of optical remote sensing, and after the basic of optical remote sensing and how to retrieve radiometric indices and biophysical variables. There will be a short introduction on ESA SNAP software. And after we'll stop a bit for questions. And in the second part, there will be the real practical exercise. So I will show you how to use SNAP to retrieve radiometric indices and biophysical variables from Sentinel-2 data. I will guide you through the processing, and you can repeat the processing afterwards with Amalia. I think Amalia already provided you a short guidelines, the step-by-step how to perform the exercise. So let's start to the first part.
Welcome everybody, my name is Fabrizio Ramoino. I work in ESA-ESRIN since 2011 as optical and thermal data exploitation expert. And I would like to present you a short refresher of optical remote sensing data and how to process Sentinel-2 data using ESA SNAP software in order to retrieve biophysical variables and radiometric indices for agriculture. The objective of this training is to provide you, or rather refresh the basics of optical remote sensing, explain what are the main characteristics of Sentinel-2 data. You will learn the basics of radiometric indices and biophysical variables and its usage in agriculture. I will also introduce you the main feature of ESA SNAP software and explain how to use SNAP software to pre-process Sentinel-2 data and how to retrieve radiometric indices and biophysical variables that can be used, for example, in crop monitoring. Optical satellites and instruments are passive sensors. It means that they collect information and measure radiation which originates from external source, which in this case is the sun. The part of radiation that is collected by the sensor is the radiation which has been reflected from the Earth's surface. Part of this radiation is also scattered by the atmosphere and does not even reach the Earth's surface. Human eye is also a kind of remote sensing sensor, which collects information only in the visible part of the electromagnetic spectrum. Using remote sensing sensors, for example on board of satellite, we are able to extend the spectrum and collect information in extended range, for example visible to near infrared, shortwave infrared, but also in thermal infrared. This part of the spectrum is unfortunately largely affected by the atmosphere and clouds, which are blocking the radiation by scattering from the objectives on the Earth's surface. So it's important that the satellite system takes into account effects of the atmosphere, and for example, in the data processing, we are able to remove or compensate some of these effects. For this reason, we need to pre-process the optical data in order to account for the atmospheric effects. We need to apply atmospheric correction to take into account gases and particles present in the atmosphere that can affect the incoming radiation, and we need to compensate this effect. Optical data pre-processing includes also cloud detection and cloud removal algorithms. Other pre-processing steps that may be needed to apply are the reprojection, resampling, and co-registration. A large portion of the Earth's surface is covered by clouds. Consequently, most Earth observation images in the visible spectral domain include a significant amount of cloudy pixels. An image pixel can be cloud-free, partially cloudy, or totally cloudy. Cloud detection methods can be categorized in the following classes: spectral threshold methods, feature extraction and classification, learning algorithms, multitemporal analysis, or multi-sensor approach. Before radiation used for remote sensing reaches the Earth's surface, it has to travel through some distance of the Earth's atmosphere. Particles and gases in the atmosphere can affect the incoming light and radiation. We have scattering and absorption effects. Scattering occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path. Absorption causes molecules in the atmosphere to absorb energy at various wavelengths. For further analysis, we want to use a surface reflectance product in order to allow comparison between images, allow repeatable measurements, and represent a known physical unit. For this reason, to retrieve surface reflectance, we need to add back the component lost in the atmosphere. The other pre-processing steps are reprojection. When you work with satellite images coming from different satellites, you need maybe to reproject because maybe they don't have the same coordinate system. So, for example, Sentinel-2 images are in UTM WGS84, but if you want to project Sentinel-2 images in Google Earth, you need to reproject them to Lat-Long WGS84. Resampling may be needed when you are using the data from different sources with different spatial resolution, and in order to overlap them correctly and work with the stack of data, you need to resample your images to the reference one. And further step could be the co-registration, which is very useful to perfectly overlap images and maximize the geolocation accuracy in time series analysis. Why use time series? A time series is defined as a set of satellite images taken over the same area of interest at different time, and it can be made use of different satellite sources to obtain a larger data series with short time interval. Time series of satellite observations offer opportunities for understanding how Earth is changing, for determining the causes of these changes, and for predicting future changes. Now I would like to show you a great example of optical high-resolution satellite, which is the Sentinel-2 Copernicus optical high-resolution mission, which is used for monitoring land and coastal regions. It's a multispectral instrument, which means that it's registering incoming radiation in multiple spectral bands. we have 13 bands, 4 bands at 10-meter resolution, blue, green, red, and near infrared. We have 6 bands at 20-meter resolution, 2 bands in the shortwave infrared, 3 bands in the red age between red and near, and after we have a narrow band in the near infrared. On top of it, we have 3 bands at 60 meters, and these bands are mainly used for atmospheric and cirrus correction. If you compare Sentinel-2 to Landsat, the difference is bands that Sentinel-2 operates in the red age, but we miss the thermal bands, which are present in Landsat. The spatial resolution in Landsat is 30 meters, and the revisit time that is 16 days. The revisit time of Sentinel-2 at the equator is 5 days, with 2 satellites in the same orbit, with a swath width of 290 kilometers. Here we can see the map of Sentinel-2 coverage. So practically you see that we have whole land and coastal areas covered by Sentinel-2 systematic image acquisition, and even the islands. We have 2 levels of Sentinel-2 products, level 1C and level 2A, distributed by 100 km by 100 km granules, which are the minimum indivisible parts of the product. These products are distributed free of charge in free and open mode through Copernicus Open Access Hub. Level 1C is the top of atmosphere reflectance in cartographic geometry, and level 2A is the bottom of atmosphere reflectances in cartographic geometry. So the Sentinel-2 level 2A data are atmospherically corrected. The atmospheric correction is performed by using a processor called CENTO Core. This processor is the one used in the ESA payload data ground segment, but is also available for the users. The CENTO Core is distributed via STEP, Scientific Toolbox Exploitation Platform, and it can be used as plugin in SNAP software or via command line as standalone tool. The output of CENTO Core is the bottom of atmosphere reflectances in cartographic geometry, but also we have as output a scene classification map that contains basic land cover layers including clouds. We have water vapor map and aerosol optical thickness map. Apart from CENTO Core, Sentinel-2 data can be atmospherically corrected using other different processors depending on your application. For instance, we have Maya, developed by CESBio, CNES and DLR, LA-SRC, developed by NASA, HiCore, developed by Vito, Cora, developed by Brockman Consult, and many others. Here are the example of level 1C and level 2A Sentinel-2 data. On the left you see the level 1C products, the top of atmosphere products, and on the right you have the atmospherically corrected products level 2A. You can see on the left the RGB natural color combination for level 1C, and on the right the RGB for level 2A after the atmospheric correction. You have also, as mentioned before, the scene classification map, the water vapor map, and aerosol optical thickness map. Sentinel-2 data can be used for various applications like land cover classification, agriculture and forest vegetation monitoring, water quality, coastal zone and bathymetry, regional to urban application, geology and many other. In this video we have the Sentinel-2 time series over T-Water's Kloof Dam that showed the change in the water level over 1 year time. Here we have the Lanza time series from 1984 till 2018, showing the deforestation of a Rondonian region in Brazil. Now let's go a bit deeper into data processing and how multispectral data can be used to monitor vegetation and crops. One of the main methods used for monitoring vegetation, but also soil and water, are radiometric indices. The radiometric indices are quantitative measures of features that can be obtained directly by remote sensing data by combining several spectral bands. The most common radiometric index is Normalized Difference Vegetation Index, NDVI, that is calculated using the equation presented here from the near-infrared band and the red band. Because this index is used red and near-infrared bands, it exploits in particular information about the vitality of the vegetation on the Earth's surface. It uses the fact that chlorophyll present in the healthy vegetation reflects largely near-infrared radiation. In the image here presented, you see the example of calculated NDVI. The highest NDVI is represented in green for healthy and very vital vegetation. The lowest value of NDVI is represented in blue. Another radiometric index can be calculated from Sentinel-2 data and is useful to monitor crop and vegetation status is the Sentinel-2 red age position index, which is based on linear interpolation. It is sensitive both to crop chlorophyll content and nitrogen content, and it can provide valuable information about crop and crop growth status. If you want to retrieve information about physical features of the canopy, we can use so-called biophysical variables. The biophysical variables are not derived directly from the remote sensing data, but auxiliary information are needed. There are several of them, but the ones which are more important for crops are, for example, leaf area index, FAPAR, fractional vegetation cover, chlorophyll content in the leaf, and canopy water content. In the second part of the webinar, we will show how to retrieve these variables using ESA SNAP software. In this image, you can see which biophysical variables can be used for monitoring certain features of crops. For instance, for monitoring phenology, as a first choice, you would use leaf area index with 3 pluses. And as secondary measure, you could use also FAPAR and F-cover to complete the information. The same, if you want to see the impact of pests on crops, you would also use leaf area index. Now, after this short optical remote sensing refresher, we would like to present the ESA SNAP software, which can be very useful to process optical imagery, but not only optical, even radar and thermal data. SNAP is an acronym for Sentinel Application Platform, even if it can be used not only for Sentinel, but also for the data coming from other satellites. The software is free and open source, built in common Java framework. In SNAP, it's also possible to include your own Python plugin, apart from the functionalities already provided in the software. It has an intuitive graphical user interface. There is an online help with many tutorials and even very active forum, where you can discuss with other users and also developers of SNAP. It's possible to download SNAP software freely from step.esa.int. Some statistics Recently, SNAP reached 1 million of downloads, counted since June 2015. On STEP, we have more than 1,600,000 visit sessions since June 2015. STEP is the ESA community platform where you can access the software, download documentation, and communicate with developers and expert users. As mentioned before, SNAP can be used also to process SAR mission data, for example, Sentinel-1 data. We have in the software all main functionalities to process SAR data, both detected and complex data. We have tools for interferometry, PS INSAR, together with stamps and polarimetry. The main functionalities related to high-resolution optical data, apart from the readers for Sentinel-2 or other readers like Pleiad or Landsat. As I mentioned before, we have atmospheric correction processor, level 2B biophysical processor to retrieve, for example, ESA index. We have reflectance to radiance processor. We have 3 families of radiometric indices, and we have IDPix processor for pixel classification, very useful to detect and remove clouds. Concerning medium resolution optical and thermal data, the main functionalities are visualizing spectrum of pixel extraction tools, specific Sentinel-3 and NVSAT sensor processors, optical water type classification based on atmospherically corrected reflectances. We have also IDPix processor for pixel classification, and in the next months we will have many more new features related to optical, medium resolution and thermal data. In the coming weeks, a new version of SNAP 9 will be released. We will have new functionalities included in the new version of the software that are listed in these slides. We have new functionalities for SNAP Core, Sentinel-1 Toolbox, Sentinel-2 Toolbox, and Sentinel-3 Toolbox. In this slide, you can find some important links. STEP website, where you can download SNAP, free and open. SNAP user forum, where you can discuss with other users and developers. Copernicus Open Access Hub, used for download the Sentinel-2 data. The last 2 links are related to the advanced land training course focused on agriculture that we were organizing in 2019. You can find here a lot of good materials, lectures and exercises. The last link is the link to the one of the presentation of Marie Weiss, where she was presenting concepts and methods for ESA index, F-cover, FA-par and chlorophyll retrieval. In the next part of the training, I will show you how to pre-process Sentinel-2 data. We are going to resample the data. Sentinel-2 has a multi-resolution bands, so the resampling is needed if the user wishes to combine bands with different spatial resolution. I will show you how to subset the data. As I said before, Sentinel-2 data distributed in tiles, 100 km by 100 km, and the subset is needed if the area of interest covers a portion of Sentinel-2 scene, or if only some bands are needed in the processing. This can significantly reduce computation time in the next steps. I will show you how to retrieve radiometric indices and biophysical variables, and also present Graph Builder and how to build and use a graph with your processing chain. And after using the batch processor, we will run our graph for a set of products. Thank you for your attention.
Okay, I hope that the presentation was not so boring. Do you have some questions or clarification? Or we can jump to the exercise.
Yes, I don't see any questions.
Okay.
Yeah.
Welcome everybody to the second part of the webinar, focused on the introduction to ESA SNAP software and how to use it to pre-process and process Sentinel-2 data in order to retrieve biophysical variables and radiometric indices for crop monitoring. SNAP is the acronym for Sentinel Application Platform, but as already said before, it's a multi-mission, free and open source software. In fact, we have a lot of readers dedicated to optical sensors, Sentinel-2, Sentinel-3, but also ESA TPM and commercial satellites, like Landsat, Pleiad, Rapid Eye, and many others. We have also readers dedicated to SAR sensors, Sentinel-1, and heritage mission from ESA, like MVSat URS, and also TPM data like ALOS, Pulsar, and Cosmos SkyNet. So let's go to open a Sentinel-2 product, file, import, optical sensors, Sentinel-2, level 2A. Here there is the product. We open and we select the XML file and import product. From the name of the product, we can get some information, like which satellite acquired the image, in this case Sentinel-2A, which processing level, and in this case is level 2A, and we have the date and time of the acquisition. And after, we have the Sentinel-2 tile ID that identify the tile of Sentinel-2 that are 100 kilometer by 100 kilometer in UTM WGS84 coordinate reference system. Let's go inside the file. We have the metadata, where we can find information about the product, general info, geometric info, auxiliary data info. We have the Sentinel-2 bands. In level 2A, we don't have band 10 because it's used only for atmospheric correction purposes and is not in the output of the level 2A processor, Serco core. We have the 10 meters bands, band 2, 3, 4, and 8. We have the 20 meters band that are the red H bands 5, 6, and 7. The narrow band in the near infrared, band 8A, and two square bands, band 11 and band 12, that are very sensitive to hot surfaces. The last bands of the products are the one related to the scene classification map. It's a set of masks reporting basic land cover layers like vegetated, no vegetated, water, snow and ice, and water, but also it contains maps related to cloud probability, cloud shadow, thin clouds, classified pixel, no data pixel, and saturated pixel as well. You can use this information to detect and remove no usable pixels, the one that you don't want to use in your processing. Now we can open the product, we can select the product, right click, and open RGB image window. We have different RGB image combination for Sentinel-2, natural color, false color infrared, atmospheric penetration. We are going to use the natural color. For the red, we have band 4, for the green, band 3, and for blue, band 2. This is a Sentinel-2 product. It's 100 kilometer by 100 kilometer. On bottom right of the screen, we have the pixel position, X and Y, and the coordinates, lat long, for each pixel. On the left part of the screen, we have the navigation window, where we can move the visualized window. We have the color manipulation tool. Using it, we can stretch the histogram. We have the world view that shows the footprint of the open product. In this case, we selected a product over Belgium. On top bar, we have several tools. We have the analysis tools, where you can find the correlative plot, scatter plot, profile plot, histogram, statistics. We have a layer manager and editor, vector manager and editor, raster functionalities, BandMat. Using it, the user can edit his own equation and create a new band in the product. DM tools, we have geometric, where there are some pre-processing tools like reprojection, resampling, co-registration, co-location. We have mask tools, data conversion, image analysis, classification processors, unsupervised and supervised classification, with the most common classifiers, segmentation processor, and export processor. Here we have the tools and functionalities dedicated to optical. We have several processors for Sentinel-2 and Sentinel-3, the pre-processing tools and the thematic land processing, biophysical processor to retrieve biophysical variables from Sentinel-2 and Landsat 8, 3 families of radiometric indices, one for soil, the other for vegetation, the last one for water. We have the Sanity, that is a plugin to calculate the evapotranspiration from Sentinel-2 and Sentinel-3. And we have the forest cover change processor. We have also tools for radar, for interferometry and other SAR application. Under tools, we have the graph builder, used to generate and build your own processing chain, to run it on a single image, or using it on a batch processing tool to run it on a stack of images. We have the plugin manager to manage and install all the available plugins for SNAP, including your own one. At the end, we have window. On the right part of the screen, we have the product library. Using it, you can download directly the data. There are several repositories from where to download the data, Sentinel-1, Sentinel-2, Sentinel-3. We have the layer manager. You can import your layers just clicking on the plus sign here. And as you can see, several data formats are allowed. Shapefile, RGB, image from file, and all that. We have the mask manager. Here you have all the masks included in the product, and you can create your mask clicking on the function icon and edit your own expression. So now let's go to the first step of the pre-processing, the resampling. As said before, in Sentinel-2 we have bands at different spatial resolution, and if you want to combine or work with bands at different spatial resolution, you need to resample them. Click raster, geometric, resampling, and we start to set up the module. Here we have our input and the resampling parameter. If you don't know how to set up these parameters, for each of the SNAP module, we have the help, in which you can find a brief description of the algorithm of the tool, and for some of them you will find how to set up properly the parameters. For resampling, we have three options to resample the product. By reference band, SNAP takes as spatial resolution the resolution of the reference band. If you want to resample at 10 meters, you have to select or band 2, 3, 4, or 8. By target width and height, and by pixel resolution. If you want to resample at 10 meters, you should insert 10 meters here, and you can define the upsampling method. We leave nearest neighbor. We don't save the product in order to save time, and the default output for SNAP is beam dimmer format. We click on run, and the product has been generated. The next step is the reprojection. So we select the second product, raster, geometric, reprojection. We don't select save as. In the reprojection parameter, we have a lot of coordinate reference system. In this case, we want to reproject the Sentinel-2 data from UTM WGS84 to geographic lat-long WGS84 and preserve the resolution. We run, and the product has been displayed here. The next step is the subset. In order to speed up the processing, we are going to subset the image over our area of interest. So select the last product, raster, and subset. We have the window, so you can resize to subset the product. You can resize the window to subset the product. Or you can subset by pixel coordinate or geo coordinates. In this case, we use pixel coordinate from pixel 2000, from pixel 8000 for Y to 5000 and 9000. There is the possibility also to resize the number of the bands of your product. Select one. In this case, I'm going to select all the bands of Sentinel-2 plus some additional bands. Quality arrows, optical thickness, water vapor, and zenith and azimuth mean. Some zenith and some azimuth. Okay. This is our subset. As done before, we click on with the right button of the mouse on the product, open RGB image window. With the new coordinate reference system, geographic Athlon, it's possible to export the image for Google Earth as KMZ. So right click on the image and export view as Google Earth KMZ. Now I'm going to show you how to use BandMath tool. So select the last product generated, raster, BandMath. We are going to create the NDVI. We unselect virtual and edit expression. The NDVI is defined as near infrared minus red band divided by near infrared plus red band. Okay. This is our NDVI. And this band has been attached to the product here. Here we have our band. Using the color manipulation tool, we can stretch the histogram between 0 and 1. And we can change the color. We put green for the maximum, orange for the medium value, and blue for the minimum. Now we are going to split the screen using this button, tile horizontally. And here we have the two images. One, the natural color RGB combination, and the other, the NDVI. We linked even the cursor, so you can observe that over bare soil, we have low values of NDVI, and over green areas, we have high values of NDVI. Now we are going to calculate the leaf array index, the biophysical variables. So we select the product, optical, thematic land processing, biophysical processor. Biophysical processor sent here to 10 meters. The processing parameters is leaf array index, FAPAR, and FBC. We run, okay, and the new product it's touched here. We are going to open the leaf array index. Okay. We do the same color manipulation as done for the NDVI, green for maximum, orange for medium, and blue for the minimum. And we can observe that leaf array index and NDVI are quite well correlated with each other. So over green area, we have high values of NDVI and leaf array index. And now I will show you how to build our processing chain using the graph builder. So we select the first product, the original one. tools, graph builder. By default, you have two initial blocks, read and write. Right-click on the dashboard and you can add all the modules of SNAP. The first one is the resampling. After the reproject, then the subset, and after the bandmath. So we have the raster geometric resample, then the reproject, after subset, then we have the biophysical variables, biophysical operator, optical, mathematical and processing here. We have the bandmath to calculate the NDVI. And at the end, we have the band merge in order to merge the original bands with the biophysical variables and the NDVI band. We connect the graph. So as done before, we have to set up all the parameters. So the resampling is 10 meters. After we have the reprojection, that is fine as it is. The subset, we select only the first bands. And here the coordinate to subset the image. Biophysical parameters, we are going to calculate all the biophysical variables, bandmath. We use the same expression as done before. Band 8 minus band 4 divided by band 8 plus band 4. Okay. After we have the band merge. And the right block. I forgot to put even the subset in band merge. Okay, now we have all the bands. And the right. You can or run the graph on the single image, or you can save the graph. I already saved here. And use on batch processing. Save this one, okay. Close everything. Tools, batch processing. You can add all your images. Here, I will add directly the zip files. Okay, all the files have been added here. And after, you can load your graph. Here it is. So we have all the Sentinel-2 data as input. We have, should be 17 files as input. And we have all the blocks of our graph with the parameters that we set up before. Using this tool, it's possible to apply your processing chain on a stack of Sentinel-2 images. It's quite fast, and it will help you with to apply the same processing chain at each file. I would like to thank you for your attention, and
okay.
So now we have 30 minutes where you can start repeating the steps. The link to download the step-by-step guide is in the chat. And I will be going around helping. And Fabrizio, if I have a question that I cannot answer, where are you? Then I will ask you. Okay?
Yes.
Okay. Good. So like Francesco was saying before, you will see in your desktop a folder called 3_agriculture or something. And that's where you find the input data, but there's a lot of them. So when you come to the batch processing, don't do the batch processing with everything. Just do it with 2 or something. Otherwise, you can have problems. So we have a question. Do you hear me?
Yeah, so the question is that when you drag this arrow to right tab, then it gives automatically this name Biophysical OP. And then when you run it for the batch, it sort of gives the file name like this and then rewrites the same file for each image. So how to change it just to make it like for each file custom?
No, actually, when you run the batch processing, it will take the input name, and each image that you give as input will be renamed based on the input name.
Yeah, well, the question why I'm asking is because I did that and it rewrite the same name.
The same name?
Yep. That's why I'm asking, because I also was thinking that it will do like before the specific name of the input file, but it didn't.
Yeah, because in the past there was an option on the graph builder to avoid this kind of issue. Let me open Snap.
No, I'm just saying.
Amalia?
I'm actually going to ask him. Yes.
Yeah.
Yes.
Can you please tell to the guy that was asking the question before to rebuild the graph without changing the name at the end when he write in the right without changing the name.
Okay. Okay,
Yeah.
he hears you, and I think he's actually redoing it.
Okay.
Yeah. Okay, so are there any questions that we can help solve right now? Otherwise, you can continue later on after the course, and if you have any problems, you can come to me or to Fabrizio.
Yes.
Yes, if you are happy with that. Okay, I think.
Yes, I will be around.
Okay. Okay. So that's it. Thanks a lot, Fabrizio. Where am I looking? Thanks a lot for being with us today and for accepting to help us so last minute. We are lucky that we could have your help today, and thank you so much.
Okay, thank you.
Thank you. Have a nice continuation of the training.
Okay, so now we go for the coffee break. It's half an hour. And then we go with the Jupyter Notebook part, and I will put the link to the Jupyter Notebook in the chat soon. Okay, that's it.